Okay, I'm just launching a poll. I'd like to just get everyone's feedback on this. So, because we're dealing with neural networks, it's almost synonymous with derivatives. So I just want to see how many of you have experience with derivatives or have been exposed to it. If you could just participate in the poll, that'd be great. Bianca, regarding your question, I have no idea regarding that. That's the IT team that needs to make that change. Yeah, sorry. Maybe they just left it there and they left it open for submission until, the revised date. But that isn't going to affect anyone, I think. All right, so I'm just checking the poll. Oh, it's almost 50% have and 50% haven't. Okay. All right, so it is going to be a bit of a challenge today, but I'm going to try my best to try and explain it for those that haven't done derivatives. But derivatives are essential for neural networks. If you have to understand the methodology behind it, there's no going around not understanding derivatives, because derivatives are what update the parameters and make that model work. All right, but instead of me talking, let me just share my screen and give you some context what I'm talking about. Okay, if you can't see my screen, let me know. I'm sharing iris dataset highlight in the front here. And then I'm showing you my diagram of the neural network. All right, but if you can't see it, just let me know. Okay, some context of what a neural network is. So some people say that a neural network was designed to replicate the human brain. And then there's another school of thought that says otherwise. I don't know what my opinion is, because to be honest, I'm not not a medical doctor or physician, so I don't really understand exactly how the human brain does work. So I'd have to know that in order to tell you that this replicates that. So I stay out of that conversation. And all I will say is that a neural network is another predictive learning algorithm. It just does it in a different way. So it does it using an input layer, and the input layer is basically what's given to you, right? That's nothing you need to calculate. That's the data that you have, all right? So if you look at those three orange circles on the left, right, those are think of that as just three variables, right? That first circle could be the age of an applicant. The middle orange circle, that could be, let's say, their income, and then the last circle in the bottom could be, their level of education. And what you're trying to predict is, would they take up a product? All right, so that's what you're trying to predict in the end in terms of classification. But it doesn't only have to be classification. You could actually be trying to predict an amount. So it could be a regression problem. So neural networks can be used for both classification and regression. So the orange circles are what's given to you, and everything in between, basically all the green circles, is the computation and the math that goes on in the background. All of that happens, and then it throws out a probability or a value that you're interested in that red circle in the end. That's why it's called the output layer. And the hidden layers are the green circles. Now, this diagram that I'm showing you, this neural network has three hidden layers. One, if I can, 1, 2, 3. All right, it has three hidden layers. So the more hidden layers you have, the more complex that neural network becomes, and the more intense the computations become. All right. Typically, to get the most out of neural networks and to get the benefit from it, we use more than one layer, more than one hidden layer. and it makes it more powerful and more effective, right? The more hidden layers you have, there is a point where increasing more layers is just not going to add value, and you may want to decrease that. But more than one is generally the guideline. However, in this session, I'm only going to explain it to you using one layer, because if you just understand the concept for one layer, you can extrapolate that result for more, right? The idea is for you to understand how it uses a hidden layer, because then to expand that idea to more hidden layers is going to be very easy. All right. So let's move on to the next slide. Okay, before I go on to the next slide, the other thing I wanted to point out in a neural network is how it works is it actually does the whole operation using two propagations. And what I mean by propagation is just a fancy word to say it does calculations going towards the right, and that's called forward propagation. All right. So when it does the calculations moving in this direction, we'll call that forward propagation. Okay. Propagation. And forward propagation, all it does is it basically tells you, okay, how close are we to the actual value? Like how close is our prediction to the actual value? That's what the forward propagation does. Once you determine that, then we have the backward propagation. So as the name says, we start doing calculations going in the other direction, this way. This is the backward propagation step. And I'll explain what that's used for. All right, so the backward propagation, what it does is it looks at what the result, the prediction was compared to the actual value. And then it starts updating the model. It starts updating all the parameters behind it to improve that prediction. So your forward propagation will compute your prediction. It'll look at how different it is to your actual value, all right? And then it communicates that to the backward propagation step, where we start doing calculations to update the model. Now in the backward propagation, that's where we start using derivatives. So derivatives come in here, okay? Which is why it's important that you understand derivatives in order to understand the backward propagation step. All right, so just keep that in mind, and that and how the forward propagation and the back propagation fit in. Now, when I say how far off our prediction is to our actual value, or how big that mismatch is, generally what we talk about is called a loss function. That loss function basically tells you that, all right? It compares your actual value to your predicted value, and the value that comes out of that function tells you how far off you are from your prediction or not. All right. So now let's move on to the next slide. And yeah, please feel free to stop and ask me any questions. I will pop back to the chat now and then to see if there are any questions. Just give me a second. Okay, all right, cool. Now, in this slide, what the benefits of neural networks are. If I just draw your attention to this diagram here on the right. Now, I'm sure a lot of you have seen the differentiation of what linear data is and what non-linear data is, because you've mentioned that in your first assignment. So I assume that you know what you're talking about there. But I'm just doing this diagram here again to kind of illustrate non-linear separable data. So this diagram here, if you look at this one, this data is highly non-linear because you can't really draw one straight line that will clearly separate the blue and the red dots. You have to kind of create some wiggles or some other irregular patterns in order to separate that. And the same thing goes for the diagram on the left, all right? So why I have this diagram here is to show you that neural networks are quite effective at actually separating this data. And the more hidden layers you have, the better your chance of handling nonlinear data, all right? And so how the computation works is you'll start off with your predictions on the left here. Okay, just give me a second. I'm going to try and rotate my tablet and see if the screen improves. Yeah, I think it's better. Now I'm going to go this way. All right. So the x's, those are our variables. Like that example I gave you earlier, you know, x1 could be age, x2 salary, etc. You could have a lot more than one variable, which is often the case in the real world. And each of those variables have a weight associated with them. So that's what these w's are. So if you have one x variable, that w1 will be associated to x1. Similarly, for x2, you'll have w2, etc., etc. All right. Now, this a, I think, is annoying. All right. So what the weights are is, think of it like it tells you how much that weight, sorry, it tells you how much that variable should contribute towards a prediction. So let's say age didn't play such a big factor in whether someone would buy a product. And in that case, that W1, which is associated with X1, which is age, will be lower. And that's what your weights tell you, right? Your weights tell you how much a variable should contribute towards a prediction. But determining how much that contribution should be, in other words, what that weight should be, comes down to the backward propagation step. Every time you do that backward propagation, it updates those weights, all right? And we'll get into the calculations in a second, but just keep in mind that these are the parameters I talk about that are being updated when you use the backward propagation step. Okay, so these are updated, right? And what this sigma sign here, all right, that's the math symbol for sum. So what it's doing basically, all it's doing is, let's say I just had three variables, right? If I had x1, I had x2, and this was x3, right? If I just had three variables, so I would have three weights, w1, w2, and w3. So what that sigma does, all it's saying is that multiply each weight by their corresponding x value. So it'll be x1 times w1. Then do the same thing for x2. It'll be x2 times its weight, w2. And lastly, the third variable, x3 times the weight, which is w3. And then you add them up. And that's what that sigma is telling you. That's what happens there. You multiply the weights by each of its associated input variable, and then you add it up. There's a little extra term that's missing here, and that's called a bias, right? So we add a constant here called b, and that's called the bias. The reason why we add the bias in is because it allows us to shift our values up. That means not every value has to pass through 0 for every x variable. It allows us to shift the math, in other words. All right, so that b is just a bias term, and that's why we generally use b to represent it. Right, you'll kind of see that it resembles a straight line here, you know, and you've done regression before, so you'll see that this kind of resembles a regression equation in a way. All right, you got your intercept and you got slopes with each x variable. All right, so that's what happens here when we talk about the sigma. Now in this symbol here, you see it looks like a kind of an S. Now, a lot of you might be familiar with the sigmoid function because you would have covered that for logistic regression. Now, the sigmoid function, what it does is if you give it any value, what it does to that value is it'll compress that value between a value of 0 and 1. All right, so the sigmoid function, and we generally represent it with a symbol called sigma, right? Sigma, it takes in any value that you give it. So say you give it an x value, and what happens is it passes it into this function here, e to the minus x. And if you give it a whole bunch of x values and then you plot the corresponding output that you get for it, you will get a graph that looks like this. That's why you see that, all right? Now, what this part is, and this is kind of the huge advantage of a neural network, and it's what makes it predict data that looks like this, nonlinear. It allows it to separate data that doesn't really separate using a straight line. And this is what we call an activation function, right? You may have heard this term, but activation functions are what enable neural networks to handle nonlinear data. So this sigmoid function is one example of an activation function. So what happens is you'll do this calculation here in this sigma step, the sum step, all right? And then this result, let's just call it Z. We can call it whatever we want, but we'll stick to the general notation. We'll call it Z. That result gets fed into your activation function. And then once it goes into the activation function, whatever comes out of that will follow through to your output finally. All right, that's the operation of a neural network. Okay, any questions before we move on? So far, so good. Okay, all right. Okay, let's move to the next slide. Okay, so this is essentially what I've showed you earlier. I actually did pretty much most of the drawing already. So you kind of get the idea, right? So that whole sum, that Z, the mathematical notation for it is this here. All right, you're summing up the products of the W's and the X's, and then you would generally have a bias term here, right? Sometimes there isn't, all right, but most of the time there is a bias term. And if it doesn't matter, it'll automatically get set to 0 when you start doing the back propagation step, right? It'll find the optimal value for B as well. So remember the back propagation, what it does, I'm just gonna write it here. Oops, propagation. It updates your W's and your B. It updates the W's and your bias terms. Right, so this is just one hidden layer. And if you have another hidden layer, hypothetically, let's say you had another hidden layer here, all right? This hidden layer would have its own W's and its own B's. So the more hidden layers you have, the more of these weights and these biases you have to update, right? It becomes more computationally intensive. You know, obviously you're not going to have to, you know, when you're actually using neural networks in practice, you're not going to be doing these calculations manually. It happens in the background with software, but it is useful for you to understand the general idea of what's going on in the background. Okay, so let's move on to the next slide. The generalization of the math that I just did with you is this here, right? We won't draw too much attention to it. It's just, you may do it more when you're doing data science, but I just put it here so you kind of understand. If you do read any books that give you this notation, then this is what they were talking about. It's what I explained to you earlier, all right? This is your activation function. The L's, you look at these subscripts, sorry, these superscripts, these things on the top here, and you know they may become intimidating, but it's not. All that L is it tells you which layer are you in. Are you in the first layer? If you're in the first hidden layer, then that L is 1. If you're in the second hidden layer, then the L is 2, etc., etc. So that's why it's written like that. Okay, that's all the L represents. The more hidden layers, the more L values you have, right? And like I said earlier, each of those hidden layers have their own weights and their own betas, which is why you see that here like that. Okay, and they have their own activation function as well. All right, so nothing new here. It's just kind of notation that's different. Okay. Don't worry about this one. Kind of explained it. I don't want to confuse you anymore. Here, there's 3 activation functions that I've mentioned. These are the most popular ones. There are other ones, but these are the most common ones. The ReLU function is quite often used, all right? So yeah, it's worth focusing on that as well. And then you get the sigmoid, which I covered earlier, and then you get the tanh function. These are the 3 types of activation functions that you have. In the example I'm going to take you through, I'm actually going to use the sigmoid as an example. But keep in mind that there are more than one activation functions, right? But these are the three most popular. Sigmoid, you may want to ask, okay, when do you use which, okay? Now, you know, it's in practice, excuse me, it's generally difficult to know beforehand which activation function you need to use. And in what you generally be doing is you'd actually just be doing trial and error. You'd actually try sigmoid, see if it gives you a great result, and you'll try the other two to see if you could beat it. All right. So you wouldn't just restrict yourself to one activation function. But the one thing about the sigmoid function that you should know is if you have a binary classification problem, that means you're trying to predict a yes or a no, right? The sigmoid function is the function that you would generally use in the last layer, right? Because you want a probability to be returned. And that probability will represent whether it is that target value of 1. All right, so for binary classification, sigmoid is useful in your last layer. Right, just make a note of that. Okay, so I kind of explained it to the whole idea of a neural network. But like I said earlier, in order to understand the back propagation step, it's very important that you understand how derivatives work. Now, derivatives is not generally something you can just teach in an hour. It's sometimes allocated an entire semester for that. And okay, don't look at the slide. I know it might be confusing and intimidating. I'll talk you through what you need to know for derivatives. Okay, so ignore what I have here. All right, and just listen to what I say and what I'm going to write here. All right, about derivatives. Now, what are derivatives? Why are they important? Okay, derivatives is pretty much the foundation of calculus. And if you're not sure what calculus is, you should read up on that. You don't have to understand it, but calculus is probably one of the most important breakthroughs in mathematics. And that if we didn't have that, you wouldn't have the machine learning that you're doing today, because derivatives are pretty much used in the background of almost everything. All right. So derivatives essentially tell you how one variable changes when you change another variable. And very often in the real world, you have that. Something affects another thing, but you want to know, if I change this one thing, how much would it affect the value that I'm interested in, right? So if you had a machine, right, you had a machine and you could change the setting on this machine, right? But this machine, what it does is it, let's say it produces a product, right? And you want to know, if I change the setting on this machine, by how much would it change the output? Okay, so turning the knob on this machine by this much will change my output by that much, and that's derivatives. Okay, so it tells you the change of how one variable will affect the change in another variable. And the calculations, so I'm going to give you a simple example right now. Okay, if you had two variables, right? You had a y and you had an x, and they were related like this: y is equal to x squared. And if you wanted the derivative of y with respect to x, we would write it like this mathematically: dy dx. That means the derivative of y with respect to x is equal to. Now, in this example, the steps you do to find this derivative is you look at the exponent and you multiply the entire term by that. So it'll be 2 times your x squared, and then you subtract 1 from your exponent. All right, so you're left with 2x. That's the derivative. It gets more complicated than that, but essentially you can find derivatives in a very systematic way. Another example, if you had x to the 3, right? So if you had x cubed, and if you wanted the derivative of that, then it would be 3 times x to the 3 minus 1. And that leaves you with 3x squared. Right. It gets a bit more tricky, and I'm not going to explain this result because this is kind of like a 20-mark question in an exam. Or maybe I'm exaggerating. could be 10, but obviously you're not going to get tested on this. You may have heard of ln, or log of functions, or log of a variable. So in other words, if you took the natural log of, say, x, and you wanted the derivative of this, then the derivative of this is 1 over x. And I'm mentioning this now because we are going to use this, all right, in our example. Okay, so, and what this derivative tells you, it tells you how much changing x will affect your change in y. You've also heard of derivatives when you've worked out the gradient of a line. Okay, so when you worked out the slope of a line, remember your equation of a line is y equals mx plus c. Whenever you had to find this slope, what you essentially did is worked out the derivative, right? Because it tells you how a change in x affects a change in y, right? Okay, so I think that's about as much as I want to go into derivatives. I'm obviously going to go into more in a bit when I'm talking about my example. So let's just get there. Okay, now we're going to expand how we calculate derivatives using something called a chain rule. All right, now some of you may have heard of it, some of you may not. Essentially, what a chain rule does is it's used to calculate derivatives, but it's used when you have nested functions. Okay, so what do I mean by nested functions? Okay, before I talk about functions, let's just kind of talk about what I mean by that in the real world. Okay, so remember the example I spoke about. You have this machine and you turn the knob and that changes how the machine operates, and then it also affects what your change in your product is going to be. So now what happens is you have the knob, I'm going to call it K, and then you have the machine, and then you have your product, right? So you may not be interested in how the machine changes. What you're interested in is if I change the knob by a certain amount, how is P going to change, right? But in order to do that, you have to go through M. You can't go straight to P. You have to, in order to find out K is related to P, you have to go through M. So you want the derivative dk with respect to P. You want that, but there's this M that's in between. So you can't really get that derivative directly. And how you have to do it is by using something called the chain rule. So then that becomes dk. Now you'll see there's an M in between, right? So it means you have to find K with respect to M first, and then you find the derivative of M with respect to P. Sorry, dP. And if you can kind of treat it as fractions, okay? Just to help you understand, because you can see this numerator cancels with the denominator, and you're left with what you have on the left-hand side, all right? You can see it like that. If it helps you understand it. But this, what I've just done here, this is the chain rule, all right? In order to find the derivative of one variable to another, you actually had to link it to derivatives of the variables in between. And that's what the chain rule does. So that means, what it means is, you have to get this derivative first, then you have to get this derivative second, and then you multiply it and you would have the derivative that you were interested in the first place. That's what the chain rule is, okay? So the more variables you have, the more derivatives you have to string together. So for instance, let's say I had, let me just erase this. Sorry. Oops. Okay. Let's say I'll start with Y. Now Y is linked to G, and G is linked to F, and finally F is linked to X. So now if I want the derivative of Y with respect to X, which is right in the end, all right, I can't get it directly. So in other words, if I want derivative of y with respect to x, I have to first find y in relation to g, so it'll be dy dg times, then it'll be how g is related to f, so it'll be dg df, and then finally how f is related to x, so df. That means just to get this derivative that I want, I have to work out 1, 2, 3 derivatives. All right, so the more functions or variables you have in between, the more derivatives you have to work out using the chain rule. Okay, so that's my takeaway for the chain rule, and we are going to use that in our back propagation step. Okay, enough about that. Let's go to an example and put this into work. Now I'm just going to check the chat. So far so good. The same as stepwise regression model. Timeka, which part of the stepwise regression model? Which part of the neural network, I guess. So just keep in mind, neural networks can actually be, it can become the same thing as a regression model. If your activation function is just a straight line, the neural network actually just becomes a regression model. That's the only difference between a neural network and a regression model, is when the activation function is a non-linear function. That's what makes it different. Okay, sorry. Did you want to elaborate on your question? But if it answers it, yeah.
No,
Perfect.
thanks. It makes sense.
Okay, no problem. Good question. All right. So now, simplest example of a neural network. So my example that I'm going to show you is it's only going to have one input variable, one x variable, x1 on the left, right? And I'm only going to have one hidden layer, right? So one hidden layer, one variable, and one output layer. We are going to use a classification problem, right? But the same thing applies for regression, right? But we're going to use a classification problem. So this is the structure of my neural network, right? What you see on the left here with these circles. All right, structure, you'll often hear the term architecture, and it's the same thing. Architecture is basically the structure of your neural network, right? How many hidden layers, how many variables you have, excuse me, what activation function you have, and even what loss function you use. All right, okay. So, excuse me, this, what you have here is before the hidden layer. I'm just going to put before H, so that means before the hidden layer. Everything on this part is after the hidden layer, after H. Okay, so what we're going to do now first is we're going to assume some values, all right, for your X and Y, so we can actually just do some calculations and illustrate it. And I'm going to take you through the forward propagation step first. So this example of data, we're going to assume that our actual Y value, right, the known Y value, and that could be whatever we're trying to predict, is this person going to take up a product or not, right? Is that person going to default on a loan or not, or etc. We'll assume this data point, this observation, the Y value is 1, okay? And the input variable, right, the variable that we're using to try and predict it, is x1, and it has a value of 2 for this observation. And then we do need to initialize the W's and the B's. In other words, our weights and our biases. We initialize it, and in this example, I'm just going to initialize it to these values, all right? But it's going to get updated, right? As soon as we start doing back propagation steps, it's going to get updated, right? But when you start working with Python, you don't have to worry about initializing it because it does it for you, all right? But just keep in mind that it does have to be initialized. You do have to set it to some value in the beginning. So that's our W1, our bias, B1, W2, and B2, all right? So your W1 and B1, this is before H before your hidden layer. And then here, this is what happens after H. Okay. All right. Our sigma, our activation function that we're going to use, we are going to use the sigmoid function. As I mentioned earlier, I'm going to use the sigmoid, but you know that it can be other activation functions. But for this example, we're going to use the sigmoid activation function. All right. So now this is the structure of our network. This is our data. Let's begin the forward propagation step. Now the forward propagation step, it's the same diagram on the top. What we're going to do is we're just going to plug the values in. So we're going to start from the left, as the name suggests, forward propagation. That means you start from the left and you start moving to the right and start doing the calculations. Can just go away. There we go. We're going to start moving to the right. So we know our x1, and that value is 2. Okay, remember, that's our data point. We're going to plug that x2 into our z function here. So we know what w1 is. There it is here. And we know what b1 is. And we feed those values into our z1. All right. So you got x1 is 2, your w1 is 0.5, and your b1 is minus 0.2. You plug that in, and you get a value of 0.8. So your z1 is 0.8. Okay, so that's our first step. So we've started moving from left to right. Next, okay, we're going to go to this part here, your activation function, all right, your output from your hidden layer. So remember what we said, we're using the sigmoid function, right? So the sigmoid function, this is the function, all right? So you just plug in your z into that. So now the next step is we're going to take this 0.8 and we're going to feed it into our activation function here. There. All right, you feed that into the activation function and you get a value of 0.69. There we go. All right. Now we've done the step. We've done the step. Okay. Next, we are going to work out Z2. Okay. Now this is the part after our hidden layer. So we have our weights after the hidden layer, which is these values, right? 0.8 and 0.4. So we just plug all of those values into here. All right. So that's what we're doing here. We're feeding all of those values into this equation here. So you can see everything feeds into the next step. That's what's happening here. And then you get a value of 0.5. So that's our Z2. Okay. Now, lastly, to get our predicted value, because we're doing a binary classification problem where our Y value can take 0 or 1, we're going to use a sigmoid function to give us a probability in our output node. So whatever we get in this step here, we're going to feed that into the sigmoid function, which is why we've done that here. And you get your probability. That's your 0.54. Okay, 0.54. So you've done everything to get your prediction. And now, like I said, with the forward propagation, what it does is it computes the prediction and then it looks at how far away you are from your actual value. Now, there's different ways you can compare your actual to your predicted value. In other words, there are different types of loss functions. And you can choose from a couple of them. But for my example, I'm doing what you call the binary cross entropy loss function. Basically, I'm using this function here, which tells me how far away my predicted value is from my actual value. This is the function for your binary cross entropy loss function. I'm going to represent it by L, okay, because this is simplified. Instead of writing binary cross entropy, whatever, I'm going to write L, right, just to make the notation easier. And that's the formula for it. So it means if you got your actual Y, you're going to plug it in where you see Y, and your Y hat is your predicted value. That means what you got here, right, at this step. you're going to feed that in to the equation. All right, so you do that for your y and y hat, and that's what I'm doing here. When you do all of that, you get a value of 0.62. So that tells me what the difference is between my actual and my predicted value. And so what you're doing here is you kind of, the bigger that value is, that means that's how far away your predicted value is from your actual value. So you want to minimize that. Your loss function is always something you're trying to minimize. So in other words, you're trying to close that distance between what you're predicting and what the actual value is. Right? So that's my 0.62. So I'm going to show you an Excel, which I'm obviously going to share with you. And I want you to actually work through it. All right. So everything I showed you here. All right. So if we start, this is what's given. I'm just going to ignore the first column because I'm going to get to that in a second. This is what's given to you, your input. Right. We're given a value of 2. Your target is 1. We initialize our weight and our bias. And we started doing all these calculations. Right. We initialized W2 and B2. Let me do all these calculations. So everything that you see shaded in blue, that was the forward pass. You did everything here. And this first row is what we just did now, up until here, L, where it's the last shaded blue cell. That means we computed our loss function here. All right, so I'm doing it here in Excel, which I'll share with you. All right, now after this, we are going to do the backward pass, okay? And now to do the backward pass, we are going to have to use derivatives. All right, so this brings us to the end of a forward pass. Now let's move to the backward pass. Back propagation. All right, so I'll talk you through all of this. I know it's quite busy and I don't want it to seem intimidating, right? So I'll try my best to take you through all of this. So we've done the forward pass. Okay, we've went from the left to we went from here to the end. Now we are going to work backwards. We are going backwards and we are going to update our W's and B's. Now, to do that, remember we are going from right to left. So the last thing we calculated in the end on the right is our L value, our loss. The value that we computed before that was our predicted Y value, in other words, our Y hat. And then before that, we calculated Z2. Before Z2, it's W2. So if you look at this diagram here, it's the same thing. I'm telling you the same thing that you see on this top diagram. I'm just simplifying it to show you how they're related. So you have L, you have Y, you have Z2, and you have W2. Now, if I wanted to update W2, I would have to find the derivative of L with respect to W2. And this is where the chain rule comes in, all right? Remember, to go from L to W2, I'd have to use the chain rule and get the derivatives. Now, to do that, so let's do it going this way now. So if I want L with respect to W2, so I'm going to write it here. I want DL with respect to W2. That's going to be DL dy hat, because that's the next one. Then I need dy hat with dz2, and then lastly dz2 with dw2. Oopsie. dw2. That's the amount of derivatives I have to work out just to get this. All right. So now to do this, I'm going to break this up in steps. I'm going to do this one first. This one here. We'll do this first. All right. So I'm going to erase this part here. All right. Now, this part here that I'm doing first, this is the results. But I'll explain, I'll do the math now for you, okay, and take you through it. So just give me a second. So I'm going to create a whiteboard and I'll take you through it. Let me see if this it's fine. Give me a second. I'm going to create a blank whiteboard, take you through it. All right, okay. So, like I said, the first one I'm going to calculate is dl dy hat. Okay, now what exactly is L? I'll rewrite it again. So our L is our loss function, and it's L equals to minus y ln y hat plus 1 minus y ln 1 minus y hat. Close brackets. That's what our L is. Okay, that's the binary cross entropy loss function. Now I need to find the derivative of this function here with respect to just the y hat values. Now, if you recall earlier, I told you that the derivative of any function with a ln in it, and if you had x there, it's just 1 over x. Okay, I didn't prove it, and I definitely can't prove it in this session. But you can easily find the proof for this, and if you're really interested, or you can just use the result, which is what I'm doing now. Okay, so if you take the derivative of ln with anything in front of it, it's just 1 over that variable that's in front of it. Okay, so now if I'm going to find the derivative of L with respect to y hat, I need to apply the derivative to this function here. Now, a derivative, if you were going to find the derivative of x squared plus x cubed, you could simply, if you wanted to find the derivative of both of it, you could find the derivative of each of them. So that means you could find the derivative of this first, then this, and then just add it. So in other words, you can apply the derivative to each of them if there's a plus or minus sign. And if you see this function here, you do have that. You have a plus there that separates these two parts. And that's what I'm going to do for my derivative. I'm going to apply it to each of them. So the derivative of L with respect to y hat is equal to minus y, the derivative of this part here, because this is the only part that has y hat. So I can pull out anything that doesn't have y hat as a constant, right? I can take it out of the derivative part, plus 1 minus y, the derivative of ln 1 minus y hat. Okay, so let me clear this part here. Okay, now I use this result. Okay, this part, because I'm taking the derivative of ln of that, it becomes y 1 over y hat. Okay, plus 1 minus y, then the derivative of this, which is just 1 over 1 minus y hat. And just one more note, because this is 1 minus y hat, I have to take the derivative of this again, because this is a chain rule. I'm applying the derivative to the ln of it, and then I'm applying the derivative to this part in the denominator again. So it's minus 1. And if you simplify that, you're going to get, if you simplify this whole thing here, then you get minus y over y hat minus 1 minus y over 1 minus y hat. Okay, so now if I bring this back to our whiteboard, oopsie, where is it? Here. That's how I get this result here. Okay, that's the proof of how you get that result. Okay, so remember what I said, we were going to do this first. So check, we've done that. The next one we're going to do is this. This is second. The y hat, dz2. So we're going to do that second. Now, we need to see how y hat, the predicted y value, is related to z2. And you can see that here. The y hat, you get your y hat by using your sigmoid function. In other words, this is your y hat. You plug in your z2 and you get your y hat value. So if you want the derivative of y hat with respect to z2, you have to find the derivative of this with respect to z2. Okay, now to do that one, okay, I'm going to also do that in a separate whiteboard. Give me a second. Okay, so we have your y hat is equal to 1 over 1 plus e to the minus z2. So if I want to find the derivative of y hat with respect to z2, I've got to find the derivative of this function on the right with respect to z2. So that's dz2 of 1 over 1 plus e to the minus z2. Okay, first thing I'm going to do is I'm going to rewrite this thing here in brackets like this. 1 plus e to the minus z2 to the minus 1. It's the same thing. All right, I just wrote it on the top and I put a negative exponent. Now if I want to find the derivative, I just, following that rule, remember what I said, x squared, if you want the derivative of x squared, it's 2 times this whole thing, 2 minus 1, which is 2x. So it's the same thing I'm going to do here. I'm going to multiply this whole thing by the exponent, so it becomes minus 1 times everything in the bracket. And then I say minus 1 minus another 1. All right, so that becomes, if I rewrite this, it just becomes minus 1 over 1. Sorry, my bad. I did everything here just like this, but there's one more derivative I forgot to do. I have to do this derivative here again, because this is a function within a function. This is a 1 plus e to the minus z2. So I'm using the chain rule here. So I've got to find the derivative of everything here that I'm circling in the dotted line. And that derivative is just e to the minus z2. And the reason that is, okay, there's another rule, obviously beyond this course, that if you were going to find the derivative of e to the x, where the function is e to the x like this, then it just becomes the same thing. Okay, exponent functions, if you find the derivative of that with any variable in the exponent, it's just the same thing. Okay, so that's why you get this result here, and then you multiply it by the derivative of this part here, which is just minus 1. So essentially what happens is this entire thing here that I'm simplifying, if I simplify this here, I've got a lot of minuses and multiples, but if I just rewrite it, all I'm doing is going to rewrite it. It is simply just e to the minus z2 all over 1 plus e to the minus z2. Okay. I'm going to do a little trick here to kind of simplify this. All right. I'm going to rewrite this as 1 over 1 plus e to the minus z2 into 1 minus 1 over 1 plus e to the minus z2. And there's a reason why I write this like this, okay? This is the same thing. If you don't believe me, you can try it out yourself. Multiply these terms out, and you'll see you'll come back to this here. Okay, you can do it as an exercise if you don't believe me, all right? But there's a reason why I did it like this. And that's because if you look at everything in the parenthesis, if you look at everything I'm going to circle in green, all right? Look at this here, and look at this here. It's the same thing as your y hat, right? It's the exact same thing. So in other words, I can rewrite the derivative as y hat into 1 minus y hat. That's the derivative. And that simplifies things quite a lot, okay? So when I come back to the pack, second, that's why you'll see that the derivative of this, what you've done here, is this result. Now you know how I got that result. So you know how you got this result, and I just did the working to show you how you got this result. So you found the first part, you found the second part, okay? And if I just multiply these two out, if I multiply these two results, and what I'm saying is if you just multiply this result with this result, you will get this. And that is a very handy result because it simplifies things quite a lot. All right. So I'm going to move to the next slide. There's still one more derivative I have to get, and this is the easy one. All right. It's quite easy. I'll show you in the next slide. So this is the third one I need to get. So we're going to go here. All right. We found the first two. We found this part here. We found this part. All right. And it's just this. So we know what our y hat is. It's our predicted y. All right. And we know what our actual y is. So it actually should be, okay, these numbers should be switched around. It should be minus 0.54. That's right, 0.54 minus 1, which gives you this. So that's these two. That's the result for that. And the last derivative here, this dz2, this part here, this is quite easy, dw2. Why? Because let's see how z2 and w2 are related. If you look at the diagram in the previous page, there it is. It tells you exactly how z2 and w2 are related. Okay, so if you wanted the derivative of dz2 dw2, it's simply just the value in front of it. And the value in front of it is your sigma of z1. That's why it's just sigma z1. And we know what sigma z1 is because we did it in the forward pass. Okay, so if you're not sure, I'll just go back a slide and I'll show you what sigma 1 is because we did it in the forward pass step. Yeah, we know what our sigma 1 is. It's 0.54. So then you substitute that value and you have your derivative of L with respect to dw2. So I know it's a lot of work. It's a lot of math behind it. I do get that, but you do need to understand the process of how you're linking the derivatives to updating the parameter. Now I know I haven't shown you how to update the parameters yet, but we getting there. We need to find the derivative first before we do that. Okay, so let me show you how you update the parameter now. Now that you have the derivative of L with respect to dw2, if you need to know what the new w2 value is, it's linked by using an equation like this. So it'll be your old, give me a second, what's it? Right in another slide here. Okay, this is how you link it. So all it's telling you, it's this. It's saying, take your old W, what you had originally, and then subtract the learning rate, and I'm just going to use a symbol for learning rate, which is eta. And this you don't have to calculate. You set this. It's like a hyperparameter. You know, when you're doing random forest, you have to set the number of trees. If you're doing a decision tree, you have to set the max depth. It's not something you can calculate. It's just a parameter you set. So eta, your learning rate, is something you just set. Right? So your old W minus the learning rate times that derivative of your weight. And that's why we had to work this out. Okay, that's why we had to work out the derivative. So in our example, okay, once you got that derivative, we've done that derivative and we've got a value of minus 0.32. If you want the new W2, okay, so your new W2 or your updated weight, it's equal to your old W2 or your original W2 minus eta times the derivative. All right, so our old W2, okay, what we had initially, so I'll take you back just so you can see it. What did we initialize W2 with? Here, we initialized it with 0.8. Okay, so 0.8 with 0.8 minus eta. Now, in this example, I'm setting eta to 0.1, but you can change it to whatever you want and play around with it. But in the Excel I've provided, I've set it to 0.1. So if you look at the Excel here, that's your learning rate, right? Which you can change it. And I'll tell you what the learning rate actually does in a second, right? But I'm just showing you how the updating procedure works. So your eta is 0.1, and your derivative, which is what we just spent a lot of time trying to work out now, it's minus 0.32. So it's minus 0.32. And if you work this out, that'll be what your new or your updated W2 is, which I think is 0.83. So now you understand how derivatives are used to update your weights and your bias. So in a very similar way, okay, I'm not going to do the math now and take you through all of this because it's quite tedious. I'm probably sure you had enough of me talking about this math, but I can if you want. All right. If you were going to update B2, so your bias after the hidden layer, you would have to find the derivative of your loss function with respect to that parameter. Once you have it, then the updated beta 2 or the new beta 2, B2, sorry, is your old B2 minus eta times the derivative of B2. That's how you update it, but you have to find the derivative. Okay. In this pack that I'm going to share with you, I've done the workings on how to get the derivatives, all right? So you can look through it and try and do it yourself and just try and understand it, right? It does really help, and it gives you a really good, solid foundation for neural networks. Because if you can understand it for this simple example, you will understand the methodology behind more complex neural network architectures. All right. So I said I will tell you what eta is, okay, and your learning rate. Now, if you look at this, right, if you look at this function here, if I make eta bigger, right, if I make eta bigger, then that means I'm going to subtract a bigger amount from the old value. So in other words, I'm going to take big steps, right? So that's what your learning rate is. It's how big a step you should take. And finding the best eta beforehand is actually quite an art. There's actually a quite significant amount of study just invested in how to determine what your optimal learning rate is. But eta, it's another hyperparameter that you would try and find using something like grid search to figure it out. Just like how you're trying to find the best maximum depth for your decision tree, eta would also have to be determined like that, okay? You try different values a trial and error basically, and see which one gives you the best result, which one brings you the best prediction that's closest to your actual target value. All right, or in other words, minimizes your variance between your test score and your training score. Right, so it makes your model generalize better. That's what would give you the best learning rate or ether. So think of it as your step size and how big steps you want to make every time you update your parameters. Okay, so everything we've done so far, I've only shown you how to update your parameters after the hidden layer, but the exact same process follows if you're going to update the parameters before the hidden layer. It's just that you have to do more derivatives, because if you want to update L1, remember your loss function is right in the end. The next value is your y hat, then it's your z2, then it's your z1, then it's your w1. So you can see if I want to optimize w1, I'd have to find the derivative of L with respect to w1, and that's going to be a long chain rule. It's going to be this with respect to that, with respect to that, that, that. And that's why if you have more than one hidden layer, you're going to have to calculate more derivatives. The more and more hidden layers you have, the more computationally expensive it becomes. All right. But thankfully, you don't have to do this math manually. The model does it for you. But there is a problem with that. Now, if you notice, every time you calculate these derivatives, it's this multiplied by that, by that, by that. You keep multiplying them out. What happens if you start finding fractions? So you got a fraction here, you got a fraction here, you got a fraction here, here. What happens is you're multiplying smaller and smaller, you're multiplying small amounts together. And if you keep multiplying fractions together, the value tends towards zero. It approximately becomes zero. And that becomes a problem. Okay, that's when you have what you call a vanishing gradient problem. All right. So there are ways to kind of what do you call it, work around that, and it depends on choosing different types of activation functions that reduces that effect. But just know that a vanishing gradient problem is something that's commonly experienced with neural networks. Okay, so in my Excel that I'm sharing with you, pretty much everything I've talked you through is done here. Right, so here are the backward propagation steps, all the derivatives and their values. Then I computed the new values, showing you how to take the old value minus eta times the derivative that gives you the new value. And then you would repeat the step for the next step. And that's the next line here. Okay. And you just carry the formulas through. Now, if you look, if I use the new values for W1, okay, because if you see here, here's your new value calculated. So all I'm doing in the next line is just using those values. So your new W1, your new beta1, you're going to get different Z1 values based on these revised values, and the same thing for W2 and B2. Now, if you look at the loss value, you can see it decreased. So you kind of see how the updating works, how it brings you closer and closer to the true value. And that's how neural networks work. Okay, you do the forward propagation, you assess how far you are from your actual value, you update your parameters, your W's and your B's, and then you do a prediction again, compute the loss, and check whether you're doing better, right? And the way the updating works is it does it in such a way that it does reduce your loss function. Not all the time, but on average, it would do that, okay? That's how it works. The last thing I just want to show you is the example I showed you is just one X variable. It's as simple as can be. I've got a sheet here, and I'll show you here. This is something you can play around with if you want, and I do encourage you to do that. you'll see in this problem, we have a number of records. So it's not just one record like the one I showed you. And you have two target variables. Sorry, not target variables. You have two variables, right? You got bill length, bill depth. So we're using a data called the penguins data. All you need to know in this data set is you're trying to predict a particular type of penguin. There's only two types, so it's a binary problem, right? You can either be a Gen 2 or Adele. The names aren't important, but all you need to know is, are you predicting a 1 or a 0 using these two variables? So here you have a hidden layer, all right? And you have another hidden layer, and you have an activation function, which I'm using is the sigmoid, right? If you look at the formula, you'll see that it's the same thing as the sigmoid function I was talking about. So it does all the calculations for you here. And what you want to do is you want to work out the loss for every record and then work out what the average loss is. Because you got a lot of records now, you're going to use the average. The formula for the losses here, it's using that same binary cross entropy function. So what do you think you need to do with this formula for all the other records, right? You just need to drag it down to get the loss for everything and then get the average of this column here. And then what you want to do is, remember, the whole idea is to minimize the loss. So minimize the average loss. So you use solver to minimize this value, okay, based on your weights and your biases. So if you look at these values, they feed into the calculation, right? So if you go here, data, formula, trace dependence, okay, you'll see all of these values use the weights. Okay, so in the end, move the arrows. In the end, your prediction depends on the weight and the biases, and in the last layer, it has its own weights and biases. So all you want to do is solve this, make this minimize this by adjusting these values. Okay, so try it as an exercise. So remember, get the loss function for all of these rows, get the average, and then minimize this value based on this. Okay, you can look at the solution in the next slide if you want, but try and do it yourself and then compare it to that. Okay, so here we're using two variables to do a classification problem. All right. Okay, that's it for me. I'm done. Are there any questions? I know the math is quite heavy, but there's absolutely no way I can work around the math to explain neural networks. And that's the simplest problem as I can do. But do read up on it. One book I would really encourage you to read, especially if you're going to do data science using Python, is a book. Let me just share my screen here. Is this book here, Deep Learning with Python by Francois. I think his surname is Calais. The guy works at Google, very brilliant. And the way he wrote this book is, it's one of the less complicated books, but he explains it very well using Python. Yeah, and good analogies as well. All right, that's it for me. Any questions? The floor is open to you. And thanks for bearing with me. Nothing? Okay. Okay, I'm hoping it's not everyone being confused, but yeah, if you understood a lot of it, I'm happy. But if you have any questions, please contact me, drop me an email. Happy to help. And I'll make the recording available by tomorrow. JC?
Evening, how are you?
Good, and you?
All right. I was trying to follow you, but the meds was killing me.
No problem.
Yeah, but maybe just what I've gathered is this is supposed to be for almost non-linear kind of uh, data that we are trying to almost separate and then be able to create predictions. I want you to just maybe assist me. Then I remember when we used sigmoid, when we did logistic regression, although that one was for binary kind of data, this whole derivatives that we were doing. Because when we got to that part where you try to explain the solver, and then we got to thinking, okay, we first of all come up with these X or variables, but we almost are now trying to say, how can we get to the equation that minimizes the loss function, and then it can then lead us to the best predictions. The maths, of course, is the maths, but then basically that's what we're trying to do.
Yes. You know what, you make a very good point. You said when you did logistic regression, you use the sigmoid function. And logistic regression, it generally makes an assumption that the data is linearly separable. So you may want to, it's a good question that you're asking, but then if we're using a sigmoid for logistic regression, and that works for linear data, then why were you using a sigmoid function in a neural network that can, handle nonlinear data? And the reason is, and if I'll just kind of go to my screen here, all right, it's such a good question because this is the difference between a neural network and a logistic regression in classification. Yes, a neural network will take your inputs, right? And then it'll go to a hidden layer. And in that hidden layer, you can apply your sigmoid function. So I'm just going to put sig, yeah, so you know I'm talking about sig. All right, and if you go to your output, yeah, then you apply a sigmoid again, let's say to compress it. This neural network hasn't really added too much value compared to a logistic regression, right? It's almost similar, but here's what makes it more effective is that with a neural network, you don't have to restrict it to just one hidden layer. If I start adding more hidden layers, and that could also have a sigmoid, and maybe the next one could have a ReLU function. Now it changes it. Now when you have your output, you can, because you got all of these different layers, it makes it more complex and it can handle non-linear data. And that's the benefit of it. Each layer does not have to have the same activation function. And even if they did have, say each one of them had sigmoid, 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 by the end, you're making predictions in a very non-linear way because you're combining these layers together. That's what makes neural networks so effective. Is that okay?
No,
Great.
thank you. Thank you.
Very good question. Okay, everyone, thanks so much for joining. I really appreciate it. Yeah, and we'll chat soon. Have a good evening.
Thank you. Bye.